Okay, so in the last video, I mentioned this reaction of water onto an alkyne. And I said, if you remember what they did in alkenes, they kind of do it here as well. There's not really any difference. Okay, so what do I mean by that? Let's say that we have a carbon, 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 and a triple bond that is here. And we add water. We add water in the presence of an acid, of course, in order to make this go forward. That was the catalyst. That's what was needed. If it wasn't for that H+, nothing's going to happen, because we said water and organics really don't mix. There's not really a self-initiation period here, but the addition of the acid gets this thing going. That was a review of the mechanism. That's the same type of mechanism that happens in alkenes as it does alkynes. So what begins to happen? All right, well, if I take this reagent and I redraw it like we always do, and I break the triple bond to a double, and two sides of attachment open up, it's a symmetrical alkyne. That's why I started here. It doesn't really matter which side the H goes on. Just pick one. I'm going to go left. And then we have an OH that goes here. And then you might want to truck on and do your business. All right, but you have to stop. Stop. Don't go any further. And here's why. With waters, a funny thing happens. It didn't really happen with alkenes. And that's because a double bond broke to a single, and we added H on one side and OH on the other. But here, a triple bond broke to a double. And look at this, folks. This is a double bond that's right there. There's some extra electrons. And this is an OH group. And this OH group, that oxygen has some electrons. And they are on the same carbon. They are pretty much neighbors. So a funny little thing happens in this molecule. When I take an alkyne and react it with water, it goes to this step first, and the molecule kind of puts the brakes on for a minute, and it says, whoa, 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 we've got something kind of special that's happening right now. What we call this group, a carbon that has a double bond and an OH, we have a special term for it, and it's called an enol. Why do you think we call it an enol? Think about it. Use what you learned. Use your words. En for double bond, maybe. And I see a double bond that's right there. And ol for an alcohol. And I see an OH group that's right there. That is why we call this a enol. En for a double bond and ol for an alcohol group. The enol represents this piece of a molecule if it forms. The carbon double bond carbon with an OH on it. All right, now I'm putting the OH down. I want you to keep in mind that pointed down or pointed up at this point in time means nothing at all. So I could easily write carbon double bond carbon and have an OH that points up. That is also an enol group, all right, just to kind of cover the basics. The thing with enols, here's what you need to know about them. They are not very stable. They immediately will rearrange. And this is due to delocalized electrons. All right, so we've not really talked about delocalization in any extent at all. But we did mention localized and delocalized electrons back in the day. And we said localized were electrons that were stuck. They had to stay put. They had already rooted. That is where they were going to live their life until the point where they just kind of pass on, right? And then delocalized electrons were floaters. They were gypsies. They were going from city to city, town to town, just to figure out where they want to live life. They had no roots. They had no tie downs. Okay, so we have delocalized electrons here. What does that mean? Well, that means the electrons that were in this double bond, they saw this oxygen up here, and this oxygen's got some electrons around it, and that oxygen's electronegative. That oxygen is an electron sucker, and the carbon and the oxygen are in a relationship right now, and oxygen, all it wants is, I want. Everything that carbon gets, oxygen sucks it up. What an awful life. Carbon can't have any fun. Carbon can't do things on his own or her own. Carbon can't go out and spend money on themselves, himself or herself, right? This carbon is in a relationship where the partner is going to take everything that carbon makes, including extra electrons. Extra cash right there, a part-time gig. What does that oxygen do? Want. So these electrons can actually get shoved through and get closer to that oxygen. Okay, well, if that happens, oxygen gets to a point where it's like, oh gosh, I've got too much. I've got too many pairs of shoes. I've got too many watches or rifles, depending on if you're male or female. So I got to get rid of something. I'm running out of room. I can't take all of this. And it goes to the Goodwill and it donates. What does it donate? It donates this little hydrogen. And it says, I don't need this. This is trash. Hydrogen, you got to go. And hydrogen says, okay. So hydrogen goes away. Poor thing. But this carbon, it was just stripped of those electrons. And this carbon, it needs something right now. It feels very lonely. And good news, that hydrogen is right there. And it can come in and say, hey, you've got an empty spot. You need somebody. What about me? And this carbon says, okay, I guess you'll do. So what we see, a rearrangement. That rearrangement is due to the moving of electrons. And enols will rearrange into this. The double bond basically moves up between the carbon and the oxygen due to the electronegativity. This hydrogen that was on that oxygen's got to go, so this oxygen stays neutral. And that hydrogen will come onto that sp2 carbon that was there before. So it's a switcheroo. That's what happens. And the molecule is more stable this way. And the reason is because the electrons are closer to that more electronegative oxygen that wanted it there. All right, well, when this happens, this forms a carbonyl. We've seen this before. This carbonyl functional group is the C double bond O. That is what that references to. Well, there's two types of carbonyls that can form. One was the aldehyde, and one was the ketone. It's coming back. It's all coming back to me now. Celine Dion. Great song if you didn't grow up in the 90s. So aldehydes and ketones can form here. And I could go through and recognize that functional group and talk about that functional group and see which one begins to get formed. So to do that, we have to make sure that we understand the difference again between aldehydes and ketones. So if a carbonyl, C double bond O, has a hydrogen on one end and a carbon on the other, this was the aldehyde group, right? And if the carbonyl has two alkyl groups, one on each side, random groups, it doesn't matter, this is what we called the ketone. Now, I don't know how to name them. I do not know how to name them, and that's okay. We will not learn how to name these in this particular class. This is a second semester class. But I can at least circle the functional group and label it as an aldehyde or label it as a ketone. And you have to keep in mind that a C double bond O in particular is called a carbonyl. So, enols when they form in the world of alkynes, enols will rearrange, and they will either go to an aldehyde or they will go to a ketone, depending on the alkyne that we started with. So this is the real picture, the real mechanism of what happens when the enol rearranges. And this is actually written a little different than what I just described, because I think that the way that I describe it might make better sense to you in the very beginning. And you can visually see that happening maybe a little bit better. Oh, we just do a switcheroo. The kind of double bond moves up between the C and the O, and the H just kind of flops down onto that carbon. It actually happens a different way. So if you want to get particular and if you want to look at the mechanisms, this is how the rearrangement begins to take place. Keep in mind that acid is a requirement here. All right, so this is the acid molecule. So that hydrogen is attached onto a water. That's H3O plus, representation of the acid. And this oxygen carries a positive charge. This gives me a nucleophile and an electrophile to begin with. So remember, we said that this reaction doesn't even happen unless it was for the acid in the very beginning. So we have to bring this into consideration. All right, so my double bond, which is the nucleophile, is attracted to the electrophile, and it attacks this hydrogen. And this hydrogen says, okay, and then it leaves. So it leaves behind the electrons, and water, boom, zooms off. All right, so this double bond will end up breaking in a way because that hydrogen has now been pulled into the picture. Where does the hydrogen go? Well, that hydrogen looks at this carbon and looks at this carbon, and it says, ooh, I've got more hydrogens over here, and that's where I want to play. So it goes over to the left-hand side, and we end up with a CH2. Well, right now is the opportunity for oxygen to do what it needs to do. And oxygen says, hey, listen, before you go forward with this, now that you're in this transitional period, I'm going to take these electrons and I'm going to kind of push them in here. Oh, look, and we get a double bond that gets formed. But then oxygen says, wait a minute, I'm electronegative. I want electrons. What do you mean? So I'm going to have to get these electrons from somewhere. Hydrogen, you gotta go. So the water molecule that was formed over here swings back around and says, I'm not finished with you. And this water molecule looks at this hydrogen and it plink, plucks it off. And that allows these electrons to be shoved back to the electronegative oxygen so it can become neutral all over again. This is really how the mechanism happens. All right. Now, the other way that I've described, I think people see it maybe a little bit better. But if you wanted to be proper about it, acid is a requirement. Acid is what starts this whole chain reaction. And we have to show the acid and how it begins to form. We have to do that here. So this is the enol structure. OH onto a carbon with a double bond carbon. And this is the enol. And that enol rearranges. How does it rearrange? This is how it does it, folks. Right? The double bond's attracted to the acid. That initiates this whole chain reaction to take place. Those electrons get shoved to the water, and water circles back around. When this double bond breaks, because it's attracted to that electrophile, the electrons here shove down first. Oxygen decides to get rid of this hydrogen. Where is it going to go? Well, water's there to take its place. So water will carry the hydrogen off, and oxygen sucks those electrons in, so that way it can become neutral all over again. All right, so that's how this mechanism really takes part. So ketone, once more, it's a carbon with two alkyl groups on either side, flanked on each one of those carbons. The aldehydes, well, there's your aldehyde group. Hydrogen is on one side. It could be left or right. It doesn't matter. And an alkyl group is going to be on the other side. So there's your difference between the aldehyde and the ketone. We also have a term that we use to describe this flip-flop. And over to the right-hand side, That is your enol tautomer. That's what we call that. It is a form that shows up, and this form will rearrange. And we use the term tautomer to kind of explain that. So this is our enol form that will rearrange, and it rearranges into what we call a keto tautomer. All right, so this keto tautomer and enol tautomer exist in equilibria. That's why that arrow goes back and forth, back and forth, back and forth, back and forth, back and forth. It always does it. Flip, flop, flip, flop, flip, flop, flip, flop. It can't really make up its mind. However, it does have a preferred, and the preferred is the big arrow that points left-handed here. And the big arrow that points left-handed points toward the side of the carbonyl, and we call that the keto tautomer. Why keto tautomer? Well, in this case, it is a ketone group. I see an R group here and an R group there, so that's why we call it the keto tautomer. So enol goes to keto, keto goes to enol, vice versa in this example. All right, so that's all that tautomer means, and tautomerization means flip-flopping those functional groups back and forth. C double bond O goes to COH. COH goes to C double bond O. C double bond O goes to COH. That is tautomerization. All right. So in the next video, what we'll do is we'll do some examples, and we'll go through and we'll take a look at what goes on. We'll predict some products. We'll kind of stop midway. We'll kind of analyze and rationalize what type of products will form from these alkyne reactions with the addition of water. So stay tuned. Don't take a break yet. Come back. You're on a roll. You're learning. You're getting this. I know you are. So come back and push play.